Hi, welcome to first lecture of chemistry. So in this video, we're going to start with the right isotope notation. There are few information that you can get from isotope notation. First, the symbol of the element, which represent by the X in this case. Second, the neutron number, also can known as mass number, which represent with the symbol of A, and the value is the total number of proton with the number of neutrons. Then third information is about the proton number, and then the fourth information is the charge of the ion. If there is no charge, means that it is refer the element as the atom, and the number of proton and electron are similar. Okay, let's look at one example here. This is the isotope notation for germanium ion. So in one atom, there are three subatomic particles, which are the proton, electron, and neutron. So for this first example, we have the germanium ion. As we know, the proton number will be represented by the 32. So this is 32. If we want to get the number of neutron, it will be have 72 minus 32, which is the 40. Okay, then now we will get the number of electron. Due to the charge of the ion is too positive, so we have the idea that the number of proton is more than electron. Therefore, the number of electron is 30. How about another case? If we have germanium atom, Ge 7232. So the number of proton is 32. The number of electron is also 32 because there is no charge over the isotope notation. So number of proton and electron is similar. The number of neutrons, still the neutron number minus with the proton number, which is equal to 40. How about if there is one special case? The germanium ion gain electron. For example, we have Ge negative. So the neutron number 72, proton number 32. So if in this case happen, again, the number of proton is 32. However, the number of electron is 33 because there is negative charge here, which means number of electron is extra 1 compared to the proton, and the number of neutron is 40. Okay, we already finished the right isotope notation. So you will able to answer tutorial question number 1 up to question number 4. So now we are continue with the second objective in 1.1, which is interpret mass spectrum. Basically, this is the image for the mass spectrometer. So mass spectrometer is a device that can use to determine the number of isotopes of an element, and then at the same time we can know the mass of each isotope and also the abundance of each isotope. So how we are going to get this information? Basically, after the mass spectrometer analyze the sample that placed inside, it will come out. It will produce a mass spectrum, which will be displayed at the monitor. These are the example of the mass spectrum. Okay, so what is mass spectrum? So this mass spectrum will display at the monitor, and basically we can see like here, the mass spectrum is basically look like a graph, at where the y-axis is represent the relative abundance. In other terms, that will be considered as represent the quantity of the isotope, while the x-axis here is represent the mass of the isotope. Mass of isotope, and this is the quantity of each isotope. So for example here, there will be a isotope with the mass 70 and then the abundance is around 9 portion out of the 16 here. Okay, then after we have this information, we will able to determine the average atomic mass of the element in the periodic table. Now let's look in the details of the mass spectrum. The number of peaks is equal to number of isotope. Okay, let's say this is the mass spectrum of isotope A. So there is 3 peaks. So means that there are 3 isotopes. Okay, so for example A, so when we want to write the isotope A, we will have A70, A72, and also A74. Okay, we have 3 isotopes. And then the height of the peak will represent the abundance, which is the quantity. So means that among these 3 isotopes, 70, 72, and 74, 70 is the most abundance. So if it is, how we know that it is most abundant? Because the line shows the longest or the highest peak. And then the mass of each isotope is represented at the horizontal axis, which so-called is like x-axis. So from here, based on this information, we are going to calculate the average atomic mass . Now let's look at one example, how we're going to determine or calculate the average atomic mass based on the mass spectrum. So this is the mass spectrum that we carry forward from the previous slide. If we want to calculate the average mass spectrum, we have the formula, which I always say is Ki. Okay, this one is Ki, and then this one is Mi and Ki. Okay, so from the symbol here, this is the symbol of sum, which the mathematical operation is addition in this case. And then the mathematical operation between Ki and Mi, the abundance, Q is the abundance, and the M is the mass, will be the multiplication operation. So look at one example. So in this case, there is 9 isotope of 70. Okay, so I just use the short form, average atomic mass will equal to 9 multiplied with the 70. Okay, so this is the first isotope. We have 9. And then now we continue with another isotope, which is 72 with the mass, but the quantity is 6. So I will going to use 6 multiplied with 72. And then the last of the isotope is 74, but we only have 1. So we will use 1 multiplied with 74. So this is how I consider the sum is total up for 3 isotopes. And then each isotope have their abundance themselves, so we have to multiply with their mass. And then over the sum of the Q, Ki, again the Ki represent to the abundance. So in this case, 9, 6, and 1 is the abundance. So we have to total up, which is 9 plus 6 plus 1. So when you press the calculator, I think basically you will get the answer 71. Okay, so now we will consider of the unit, because this is atomic mass. The atomic mass have the unit of AMU. So because of the mathematical operation is addition, so you will have the total up with the mass is 1136. Okay, so 1136 AMU, and then you're going to divide with 16. Okay, abundance have no basically abundance. Let's say here we have no unit because it is relative abundance. So after that, then we will end up the final answer will be have the unit AMU. So what is the AMU stand for? Atomic mass unit. Okay, this is the smallest unit for the mass. Okay, after having the idea how to determine the average atomic mass, let's focus on the question number 2 over here. Calculate the relative atomic mass of X. Calculate the average atomic mass of J. So basically, these two looks like similar, but the working step have slightly different. Okay, so basically we already know that we are going to use the formula Kimiki to solve this problem. Okay, before we go in details to get the comparison between the relative atomic mass and also average atomic mass, just for example, question number 44(2) here. Okay, so let's say we want to calculate the average atomic mass, and that is equal of the sum of the Kimi over the sum of the Ki. Okay, so as we know, Ki is the abundance, so we have 90.48, 0.27, and 9.48. Okay, so the next one we will focus on the Mi. Mi is referring to the mass. So basically, if you look at here, just now we say the mass spectrum, the x-axis of the mass spectrum basically is represent the mass. However, when you read this question, calculate the average atomic mass of J. If the isotopic mass is 19.9924 AMU, 20.9938 AMU, and 21.9914 AMU. So if this is the case happen, we are not going to use the whole number mass, but we are going to use the mass with the decimal places. Okay, basically this 19.9924 is referred to 20. Okay, and then the 21 is the actual mass is 20.9938. Okay, while the 22 is represent with the 21.9914. So do keep in mind that if you are given two kind of mass, try to use the one with more decimal places. Okay, so now let's look at the question here. We have average atomic mass and we also have relative atomic mass. So basically the average atomic mass and relative atomic mass have similarities and also difference. Okay, we look at the first part first, which is the average atomic mass. We use the formula Kimiki. Like just now we mentioned that the mass with the unit of AMU, AMU, and AMU, but the abundance have no unit. Even though let's say it have the unit, let's say the unit is in terms of percentage, so here also have the percentage, we can cancel out the percentage. So another symbol for AMU also can be is U. Okay, so we know that 24.33 AMU is referring to the average atomic mass. So how about if the question asks you to determine the relative atomic mass? Basically, you have to use the answer for the average atomic mass and then apply the formula. This is what you learn in SPM, which you compare with the mass of carbon-12. Okay, so 24.33 AMU dy. Okay, 112 multiplied with the mass of atom carbon-12, which is 12 AMU. So in this case, the unit of the AMU can be cancelled out. 1 over 12 and 12 can be cancelled out. 24.33. So basically, these two average atomic mass and relative atomic mass are different. Average atomic mass basically with the unit, while relative atomic mass without the unit. Then at the same time, we also notice the similarity between the relative atomic mass and also the relative atomic mass, which here we will notice that the value is 24.33 for average atomic mass. For the relative atomic mass, the unit also still 24.33. So in other words to say, this step is going to make the unit disappear. Okay, that's means we try to, so in other words, it should be like we cancel out the unit. After knowing the difference between average atomic mass and also relative atomic mass, now let's move to another focus. You will notice that there are three ways that abundance can be shown in the question. Okay, this is a tutorial question. When we look at question number 6 in the tutorial, you will notice that the abundance is given in percentage. So if the abundance is given in percentage, so basically the answer, when you total up all the abundance here, it will be equal to 100 or approximately equal to 99.99 or 100.01. Okay, second type of the question which related with the abundance, you will notice that they will give you in terms of ratio. Okay, so for example means that the abundance for argon 36 will be 4.86, argon 38 is 1, and then the argon 40 will be 1432. So now next one we look at the here the average the relative atomic mass of the argon is 39.98. So this is also another way we can like briefly check whether our final answer is correct or no. So basically when you look at here, there are three abundance, 4.86, 1 and 1423. So means that this one is at the highest abundance. So if we want to calculate the average, so basically we know that the average mass will be nearer to the 40, but it will not exceed more than 40 because the mass that in the among the isotope only have 36, 38 and 40. Okay, but because of the highest ratio or highest abundance for the argon 40, so it will make the average atomic mass basically is nearer to the 40. In this case is 39.98. So the third type of the abundance will be given in form of ratio. Okay, so if make it a ratio, 3.127 basically can be write in over 1. So and then in other words to say, we also can make it in terms of ratio, 35 chlorine to 37 chlorine, which is 3.127 and 1. Okay, so for the third type of the abundance, they are not necessarily come to the 100, but you can use it any number. Okay, but just remember that again when we use the formula average atomic mass, key, so you have to make sure the key that you substitute here always represent the abundance. Okay, so in this case the abundance for question 7 is the total up for 4.86 plus 1 plus 1423, while for the abundance for question number 8 will be 3.127 plus 1, which is equal to 4.127. Okay, there are another type of question which also related with the average atomic mass. But in this case, we will notice that the question is going to ask us to determine the percentage of the abundance. No matter how, we only have one formula in this question, which the average atomic mass is equal to key. Okay, this is what I always mention over here. Okay, so previously you will notice that in the question they ask us to look for the average atomic mass, and then in the question they give us the key either in the form of ratio or percentage or in the fraction. And then the mass also will be given. So from here we know in one formula we only have the one unknown, which is average atomic mass. So we are able to solve this problem. Okay, but in this case, average atomic mass, we are still using this formula. Key. Okay, so a sample of chlorine consists of two isotopes, 35 and also 37 chlorine. So from this isotope notation, we will have the idea that we have the mass. The relative atomic mass of the chlorine is 35.5. So in other words, to say this one also is referred to the average atomic mass. So we have the average atomic mass. Determine the percentage composition of each isotope, means that we have no abundance, which means the Q is unknown. Okay, however, we still need to solve this problem again. One formula with one unknown. Okay, then now we are going to do the calculation part. But then as we know, if we say that the abundance for chlorine 35 is equal to X%, the abundance for 37 will be Y%. Okay, because based on the previous question, we know that abundance for all the isotope, they will have different ratio. Okay, the ratio will not be equally. Okay, so we also consider abundance of chlorine 35 is X, while chlorine 37 is Y. But then because of it is abundance, so we know that X plus Y will be equal to 100%. So let's say now we substitute the value into the formula. So 35.5. Okay, so the average atomic mass is 35.5 equal the sum of the key. So for chlorine 35 is X multiplied with 35 and then plus Y multiplied with 37 and then over X plus Y. Then from here we also will notice we only have one formula, but we have two unknown. This also cannot be solved because as we know, one unknown, one formula or one equation. So what we're going to do, we have to change either X or Y to another form. Okay, so as we know, X plus Y is equal to 100%. So Y will equal to 100 minus X. Okay, then we make the bracket equal to percentage. So then now we are able to answer the question. Okay, so for example now here 35.5 maintain, X will still maintain 35 plus Y is 100 minus X. So I will put 100 minus X multiply with 37 and then divide with the X plus Y, which is 100 minus X. When this happens, you will notice that we only have one unknown in this question here, which is the X. So when this happens, it is possible for us to determine the value of the X, and then after we can determine the value of the X, then for sure we are able to determine the value for the Y. Okay, after complete 1.1, so now we proceed to 1.2, more concept. The first objective that we need to define the term for the empirical and molecular formula. So to make it more simple, so empirical formula is the chemical formula, shows the simplest whole number ratio. So whole number over here is referring to the nombor bulat, simple whole number ratio. However, for the molecular formula, it will show the actual number of each atom in the molecule. Okay, so you can look at the definition based on your notes. Okay, then now in this video, we're going to focus on the determine the empirical formula and molecular formula based on the mass composition or combustion data. However, I will only show you the difference, okay? Some basic step and also the difference of the question, okay? We will more focus on the empirical formula. So between empirical formula and molecular formula, basically we are going to identify empirical formula first. Then only we will able to determine the molecular formula if the relative molecular mass is given in the question. Okay, so the third learning objective, determine a molecular formula from an experiment. This is referred to the experiment 1. So would like to highlight again, in this video, we only focus on the second objective. Okay, let's recall the step in determining the empirical formula, which you already learned in SPM. So first, we have to identify the element in the molecule, and then we determine the mass from the question. Once you have the mass, you will able to determine the number of mole. So sometimes you will notice that the number of mole maybe will be in the decimal places. So you have to multiply with a number so that it will become the whole number ratio. Once you have the whole number ratio, means that you already able to determine the empirical formula. Okay, like previously we say that from the question we need to identify the element. Then second, we need to determine the mass of each element. So basically when you go through the question, there are 3 types of question at where there is 3 different ways the mass will be given. Okay, first type of the question, the mass is given directly. Let's look at the example. We have 18.3 grams sample of hydrated calcium chloride, which contains 4 grams of calcium, 7.1 grams of chlorine, and 7.2 grams of water. So from here, then we know that the element that can be found in this sample will be calcium, chlorine, and water. Okay, so we settle for step 1. Step 2, determine the mass. From the question also already very obvious, let us know mass of calcium is 4, chlorine 7.1, and water is 7.2. Then after we have the mass, we will able to determine the number of mole by using the formula mass over molar mass. Since this is the water, so we will divide the molar mass for the water, and then we will get the number of mole in decimal place, and then we will make it to the simplest whole number ratio, means that in nombor bulat. Okay, then we will able to have the empirical formula. Okay, so what I would like to highlight over here is the term hydrated calcium chloride. Basically, next time when you see the question have the term hydrated, means that you will have a dot like here and then with ZH2O. Z here is means that we can be any whole number. Can be 1, can be 2, 3, 4, 5, and even 8 or 11 and so on. Okay, so what is the meaning of hydrated? So basically we consider it is like the calcium chloride is surrounded by the water molecule. Okay, so that's why we know it as hydrated calcium chloride. Okay, second type of the question, you will notice that the mass is given in the percentage. So when the mass is given in the percentage, like this question, ascorbic acid, commercially known as vitamin C, used to cure scurvy and may help to prevent the common cold, consists of 40.92% of carbon, 4.85% of hydrogen, and 54.50% of oxygen. When this is the case given, so normally we will do the assumption. We will assume the mass of the sample is 100 grams. Then maybe you will ask, why is 100 gram? So for example, you will going to have 40.92% of carbon in sample, okay, in the sample. So the mass of the sample is 100 gram. So if you want to find the mass of the carbon in the sample, so what you are going to do, you will say that 40.92% multiply in the sample. The sample is 100 gram. So 40.92 when percent will be 40.92 over 100 times 100 gram. So 100 and 100 cancel out. So that's why you will get the mass of the carbon is 40.92, which is exactly similar with the value in the percentage. So mass of carbon is 40.92, 4.58 and 44.5. Then maybe again you will say that, Miss, if I don't want to use 100 gram, is it possible? Yes. Basically, you can use any number for the mass of sample. For the mass of sample. But then you will recall that in SPM, your teacher also asks you to assume in 100 gram. In metric here also asks you to assume in 100 gram. Like just now we mentioned, because here 100 and 100 can be cancelled out. So basically you have no need to press the calculator. But let's say you say that you want to assume the mass is 54 gram. Possible or no? Yes. Then here you will convert this 100 gram become 54. This one also 54. So when this is 54, you are not able to cancel out with 100 here. Means that you have to press the calculator and solve for the hydrogen and also oxygen. So this will make the working step become longer. Okay, so again, we already identified the element, we determine the mass, then we are able to find out the number of mole. So after we find out the number of mole, we will going to get the simplest ratio for the whole number. But then when you look at here, the simple ratio equal to 1, equal to 1.34 and equal to 1. When this happens, we need to multiply a whole number. Why we multiply with 3 but not others number? Because when you 1.34 multiply with 3, you will get 4.02. When you round off, it will be approximately equal to 4. So the difference between 4.02 and 4, okay, the difference, okay, is equal to 0.02, which is slightly very small. Okay, so try to remark over here again. Only can round off, okay, only can round off if the difference is between 0.01 to 0.09. So 0.02 is in the range here, so that's why it can be round off. So after we round off to the whole number, then we will able to determine the empirical formula, which is C3H4O3. Okay, do remember that once you already multiply with 3, for one of the element, make sure all the element here you need to multiply with 3. Okay, the first two example that we discussed just now, basically, mainly you can see that kind of question in your SPM questions. But here now we have another type which they will show us the combustion data, which this one is very common in the PSPM, in the matriculation level. Okay, so now again we read the question. So an organic compound A consists of a formula CX HYOZ. So again, we can identify the element is carbon, hydrogen, and oxygen. So the combustion of 1 gram of sample A in excess oxygen will produce 2.52 gram of carbon and 0.443 gram of water. So from this information here, we are going to determine the mass. Once you identify the mass wrongly, then definitely to determine the number of mole, simplest whole number and the empirical formula will be wrong. Okay, so now from here we are going to know that how we are going to determine the mass of carbon, because we have three elements: carbon, hydrogen and oxygen. So we know that compound A, CXHYOZ, burn in excess oxygen, will produce carbon dioxide and water. So basically we know all the carbon is from the compound A. Okay, so how are we going to determine the mass of the carbon in CO2? Okay, so mass of carbon in CO2 will be equal to mass of carbon in compound A. Okay, this is the main idea that you need to understand. So, but because of we didn't know the mass of the compound A, yes, we know the mass of compound A, but there is three unknown, so it's a bit challenging for us to determine it. So that's why we are going to use this mass of carbon in carbon dioxide. So the mass of the carbon dioxide is 2.52, which is given in the question. Then why we use 12 over 44? The 12 here is referred to the mass of the atomic mass of carbon, while the 44 is the molecular mass of the carbon dioxide. When we do like this, then we will able to get the mass of the carbon in carbon dioxide. Similar idea will be used when you want to determine the mass of hydrogen in water. So the mass of hydrogen is 0.443. So in the formula of water, there is two hydrogen. Each of them have one with the with the atomic mass 1. The total or the molecular mass for water is 18. So when you do like this, you will be able to get the mass of the hydrogen. Okay, then again, we just want to emphasize the mass of hydrogen again basically are from the compound A. However, the mass of the oxygen, it can be in the carbon dioxide and in the water, is either from the compound A or the excess oxygen. So this is why we are not using the method which are similar with the method you calculate the mass of carbon and hydrogen. Because the question over here mentioned there is 1 gram of sample A. So after we know the mass of the carbon and mass of the hydrogen, then we leave one unknown, which is the oxygen. So the mass of the carbon plus mass of hydrogen and mass of oxygen equal to 1 gram. So if this is the unknown, so we are going to use 1 gram minus the mass of carbon and also mass of the hydrogen. When we do the calculation, we will able get the mass of the oxygen. So I believe for this part of the question, you will discuss more in your tutorial question. So basically, we already finished the first hour for the lecture. So next week, we are going to continue with the balancing redox equation. See you in next week.